In 8.4, we're going to switch from comparing means to comparing proportions. So when we are comparing two different proportions, we can do a two-sample t-test for the difference, comparing proportion 1 and proportion 2 of the two samples. So the conditions are very similar to comparing the means, but in addition to being random, independent, and large enough or normal, we have to be able to satisfy these conditions for the means. All of these quantities have to be greater than or equal to 5 in order for the two-proportion z-test to work. If the conditions are met, then our proportions, when we subtract them, look like this. We can find a weighted estimate of our point estimate by doing this. And we can find the standard error equation by doing this. So as long as all of these conditions are met, then we can find the z-score by doing the difference of the two proportions of the sample, that's what this is, minus the difference of the two proportions for what's expected, which we expect to be equal to 0, divided by the standard error, which is found by using this equation. So we're going to do that with this example. We have a study of 200 randomly selected occupants of passenger cars and 250 randomly selected occupants of pickup trucks. The 91% of passenger cars wear seatbelts and 83.2% wear seatbelts in pickup trucks. Using an alpha level of 0.1, can you reject the claim that the proportion of occupants who wear seatbelts is the same for cars and trucks? So that tells us that our H naught and our H alternative is that our proportions of 1 is going to be not equal to the proportion of the second for our alternate. That's the claim. And our proportions are going to be equal for the null hypothesis. Actually, I think I had the claim mixed up. This claim needs to be in the top one, because they're asking us if that's the claim, so that is the claim, that they're the same. Okay, let's check our conditions. They are random. They are two separate independent, because we're talking about cars and pickup trucks, they're different from each other. We need to find our point estimate. So we need to take the 182 plus the 208 and divide it by the total, which is 200 plus 250, which gives us 0.86 repeating. That means our Q is going to be 1 minus 0.86 repeating, which is going to be 0.13 repeating. Then we can find our N P bar, which is going to be 173.33, which is greater than 5, and our NQ bar, which is going to be 21.666, which is also greater than 5. So all of our conditions have been met. They are both greater than 5, so we can proceed with the z-test. Using our null and alternate hypothesis, this is a two-tailed test because of the not equals. And with an alpha level of 0.1, this is 0.05, and this is 0.05. That means that our Z values that correspond with those is negative 1.645 and positive 1.645. Now we can proceed with our standard error equation. Standard error is found by taking the square root of P bar, Q bar times the quantity 1 over N1 plus 1 over N2, which is going to be the square root of 0.86 repeating times 0.13 repeating times 1 over 200 plus 1 over 250. Square root of all of that. That's going to give us standard error of 0.0322490308. From there, we can find our Z value, which is going to be our sample proportions subtracted minus our population proportions, which we expect to be 0, divided by our standard error. So that's going to be point in our sample proportions, we have 0.91 and 0.832. Minus 0 over 0.0322490308, which gives us a Z-score of 2.418677337. That is clearly within the rejection region. Which means that we reject the null hypothesis. There is enough evidence to show that the proportion of drivers of cars and trucks who wear their seatbelts is different. You can do this test on the calculator also. So on your calculator, you're going to go to Stat, then Tests again. You're going to pick a 2-proportion Z-test, and you're going to enter the statistics. Pretty straightforward. X sub 1 is 182, N sub 1 is 200, X sub 2 is 208, N sub 2 is 250, and you're going to do a not equals P sub 2.